Hi, I'll present our work on representative time series discovery for data exploration. The goal of this work is to summarize a large time series dataset with a small set of representative time series so that the main patterns become easier to explore and interpret. Time series data are growing rapidly in many domains. The challenge is that analysts often face overwhelming data volume, which makes exploration difficult. In this traffic example, even with a relatively small number of sensors, plotting all time series together already creates a cluttered view, and the main trends are hard to see. So instead of analyzing every time series individually, we want to identify a small set of representative time series that capture key patterns in the dataset. In this example, 3 representative patterns are enough to summarize the traffic behaviors of the sensors. This gives a clearer and more interpretable view, which is important because the end user is still a human analyst with limited cognitive capacity. The basic concept is a similarity-bounded representative time series. A time series represents other time series if their similarity is above a user-specified threshold, tau. The time series that satisfy this threshold forms its similar set. This idea is important because it lets us control how strict or how relaxed representation should be. Based on this, we define the representative time series discovery problem, RTSD. The input is a set of time series, a similarity measure, a similarity threshold tau, and a coverage threshold beta. The output is the smaller set of representative time series, such that at least a beta proportion of the dataset is covered, and each covered time series is represented by at least one selected representative. So RTSD has 2 key properties: representativeness, which is controlled by tau, and minimality, which means we select only the fewest necessary representatives. With a smaller tau, the requirement is looser, so each representative can cover more time series, and fewer representatives are needed overall. With a larger tau, the requirement is stricter, so each representative covers fewer time series, but the resulting summaries become more fine-grained. A natural question is, why not just use clustering or diversification? The reason is that they do not match the RTSD objective. First, they are not similarity bounded, which means the centroids may not meet similarity threshold. Second, coverage can be limited. Cluster centroids or diversified objects do not guarantee that the required proportion of time series is actually represented. In contrast, RTSD is defined to satisfy the target coverage threshold. Third, they do not ensure minimality. That means they may select more representatives than necessary. RTSD explicitly optimizes for the smallest representative set that still achieves the required coverage. For solution, we first prove that RTSD is NP-hard, and we build a sequence of increasingly efficient methods, from greedy approximation to a learning-based solution. Greedy iteratively selects the time series that covers the largest number of still uncovered time series. Greedy with early termination, greedy ET, keeps the same greedy idea but speeds it up by pruning candidates using upper bounds on marginal coverage. Pre-greedy and pre-greedy ET pre-compute similar sets in advance, which improves runtime but uses much more memory. So to avoid trade-off, ML greedy ET replaces exact marginal coverage computation with a learned prediction, aiming to reduce both time and memory costs. ML greedy ET is trained in a self-supervised way using greedy ET labels, and then used inside the same selection framework to choose representatives efficiently. The key result is that our method, ML greedy ET, gives the best overall balance. It remains competitive in effectiveness compared with the non-learning greedy variants, while achieving much better efficiency. In particular, it achieves up to 21 times speedup and up to 101 times lower memory cost. So the main takeaway is that ML greedy ET is not just effective, but also scalable. Thank you.